For this first question, we allow a loop to fall into constant magnetic field. Let's ask, what's the direction of the induced magnetic force on the loop as it falls into the field? So as the loop just comes into the field before the top edge is in there, so when the loop is right here, it's moved into a place where there is field that points into the page. The induced field, therefore, will be out of the page. The induced field is out of the page. We'll do our right-hand rule where our fingers, let's think about the bottom part of the loop here. Our fingers are coming out of the page with our magnetic field. Our current is with our thumb, points to the right in the bottom part of the loop. So the current comes around the loop this way. So as the loop starts to fall into the field, B is out and I is counterclockwise. Then what happens as the loop is moving through the field? As the loop moves through the field like this, the magnetic field inside is not changing at all. So B and I are both 0. As the loop falls out of the field, it's going from a region with lots of field pointing into the page to a region with not very much field pointing into the page. So the induced field is into the page. If the induced field is into the page, we point our fingers into the page, our current is towards the left. So the current comes around this way. So here, the induced field is into the page, the induced current is clockwise. So that's what happens as we allow a loop to fall into a field. Next one, we have a circuit set up. Immediately after the switch is closed, what happens to this top loop? So let's ask what happens. So we'll label those plus and minus. If we close the switch, the current flows out of the positive, comes around the loop, in and around in this loop this way. So the current will flow in this direction. So this is the front and this is the back. There's the flow of current in the bottom loop. As soon as we turn this current on, this current makes a magnetic field. The direction of the magnetic field at the center of the loop, our thumb points this way, our fingers are going up. So the direction of that field that gets created is straight up from the center. So in this loop, a field has just been turned on that points up. So what's the induced field? It's going to point down. So there's the B induced. That magnetic field points down. So what's the direction of the current? Let's imagine we're grabbing the front part of the loop. The field is down, that's our curled fingers. Our thumb is the current. So it induces a current that flows in the opposite direction. So it comes around to the left on top, around to the right in the back. So there's the induced current. Now let's ask about the forces between those wires. Let's think about the very front of the loop right here and the front of the loop right here. What's the forces right here? So this is a current carrying wire. This is a loop right on top. The direction of the magnetic field right here at this point in the front comes right out of the page towards us. So we'll do our currents to the right, our fingers show the magnetic field. Our loop looks like this in 3 dimensions. So right here at this point, it comes out of the page, points at us. That's the direction of the magnetic field. So our current is this way, force is out towards us, so we'll do our right-hand rule. Your thumb is with your current, your finger is with your field, points up, and your middle finger shows the force. So there's the induced magnetic force on that wire. You could go through the same process on the back part of the loop, and what you would see is that the magnetic force also points up. So as soon as we turn on this switch, we see that this gets repelled, and this is what we did in our classroom demonstration with those jumping rings. It's exactly the same thing. So the answer to the question is yes, and the direction of that force is repulsive. Makes it jump right up. And then the last one, the induced EMF around the loop. So let's think what happens. So our graph here shows that the magnetic field is increasing as a function of time. So the magnetic field points out of the page and it's getting bigger. The induced magnetic field, therefore, must be into the page. Because the existing magnetic field points out and it's getting bigger, we want to oppose that change of getting bigger, so it has to be induced into the page. The direction of the current, we imagine we're grabbing the bottom part of the loop, our fingers go into the page, our current goes to the right. So the current comes around this way. And that's a clockwise direction. If we wanted to think about the induced potential, we would apply Faraday's law, minus d phi dt. We want to find the size of the potential. We could do the size right there. So d phi dt is d by dt of b times the area. The area is constant because that loop itself doesn't change. So we've got a times the db dt. Change in b over change in t, that's the slope. So we get area times slope. And the slope would be the rise over the run. So the area times rise over run. The area is 2 centimeters by 2 centimeters. Rise over run is 0.5 Teslas divided by 0.1 seconds. So you do that through the calculator and you get the magnitude of the induced potential around the loop.